we have to learn the language in a formal way. That's why the term formal. All the globally available languages, right? If you want to study these 4 types of grammar, 4 types of languages, you can easily implement that one. And one more thing, now you should not say that these 4 types of grammar are the best. It's not like that. Okay, they are the basic knowledge which, being a software engineer, you'll face many problems, but theoretically, whatever you want, it will be executed 99% surely. Okay, that's the short form of automata. That's it. Now, next slide, right? It's about finite automata. Just now, I have informed that there are, wait, somebody is trying to join the class. Let me just admit it. So, it's about the finite automata. Let me go back to that. Okay. This machine, right? This finite automata in short is represented by FA. And then this is of 2 types. One is deterministic. I'm not used with this handle, okay? That's why please bear with me. Non-deterministic. Okay. So this finite automata, the first type of machine is known as finite automata. This is of 2 types. One is deterministic, another one is non-deterministic. I won't be explaining what do we mean by deterministic and non-deterministic right now, because at first, let me try to explain this finite automata first. Once we understand this one, right, I'll move with this one slowly. So for the time being, do not raise any question, what do we mean by deterministic, what do we mean by non-deterministic. I'm just telling you, we'll be having 2 types of machine, that's it. So out of those 4 types of machines, the first one I'm going to start discussing it. The name of the first machine is known as finite automata. Now let me move with this slide. In this slides, right, I have written, okay, fine. Okay, state diagram. Wait. Okay, in the slide itself, right, informally, a state diagram that comprehensively captures all possible states and transition that a machine can take while responding to a stream or sequence of input symbol. So let me explain this part. When you go back and check the textbook, right, you'll find a block diagram. Leave this finite automata for the time being. If any function, in the last semester, we have already seen in digital design, sequential circuit, combinational circuit and all. So instead of discussing that combinational and sequential circuit separately, right, let me just take a circuit, let me consider a general circuit. What kind of works is being done by that circuit? We are going to provide certain sort of input. This will have certain connection within that circuit. As per that connection, right, we'll be getting some output. And then in certain simulation lab or maybe in theory class and all, you have seen in multiplexer, then register, then many AND gates connection and all you have seen, right? Let's take another one. Connect 2 AND gates, provide 4 inputs, and then join the 2 AND gates with, okay, let me move to that, this one. Let me take, okay, you're going to provide certain inputs. Let me represent by I, capital I. This is output, okay? And then this is, in case of, for the timing, just forget about this flat paper. I'm just talking about digital design. Last semester, what we did, we have done some connection in between. How the output will be generated depends on this particular circuit. And then I'm talking about circuit. I'm not talking about either combinational or sequential. Again, depending on this circuit connection, we are going to get certain output. Now, this finite automata, which is an abstract machine, right? Abstract machine. I don't know what's happening within this. I'm just considering this as a black box. I'm going to provide certain inputs here. I'm going to get certain outputs here. Some processing is going to be done here, but I don't know what kind of processing we are going to done. And then normally why we are developing, why we are running after machines. Right now I'm using this, writing pad to scribble something here. Why I need this? In order to ease my online classes, right? I'm using this. Why we guys are, running after the machine? In order to reduce our workload, or in order to solve our problem, or maybe in order to minimize the complexity of a particular problem, or maybe in order to, just bring all the all the manual work in one click of a button, maybe because of that. So many problems are there, we are going to solve it. So if you, depending on your problems, right, we are going to design this circuit, or maybe we are going to design this structure. Okay, in terms of circuits, if you want to turn off everything, when you provide 0 0, or maybe when you provide one input as 0, other as 1, and out, which gate is required? And gets to connect all the inputs and then connect that one door gate, you'll be getting a 0 as the output, as per the truth table which we have seen in the case of AND. In the case of software designing part and all, we are going to provide certain inputs, and then depending on this processing, or depending on the architecture, we are going to get certain output. So there are many problems we are going to solve using this finite automata. Okay, there are many problems we are going to solve using this finite automata. What are those problems? I don't know right now, but we are going to solve some problems using this finite automata machine. So instead of understanding this problem first, we have to understand this finite automata. Got it? Using this machine finite automata, definitely we are going to solve certain problems. Why we are designing this system means either we are going to solve certain problems, or either we are going to get certain answer which we could not able to get it by using other different circuits, or by using other algorithm. So using this finite automata abstract machine, we are going to solve certain problems. What are those? I don't know. So let me begin with this finite automata. And how to represent this finite automata? Because in the case of digital design, right, if we used to draw circuits. To remember, you used to construct a truth table. If you want to design a circuit for that one, based on the truth table, you have constructed the circuit, and then you try to check the output as per the truth table. If you're not getting in, then you are just trying to rectify that one, right? That's the process we have been following in the case of digital design. But what about the finite automata? In the case of finite automata, I've already told that this is an abstract device. But even though this is an abstract device, we should understand this machine. So we have to learn how to represent this finite automata. So this finite automata, right, that can be represented into two types. One is known as state diagram. One is known as state diagram. Another one is known as state transition table. Okay. I guess state diagram you have seen in the case of digital design paper last semester. Remember those circular thing representing the circuits, and then from this to this one level, like that. Remember, that is known as state diagram. In this semester also, we are going to use that one. Few things are to be added. When the time permits, when time comes, I'll take one example and I'll explain to it. Another one is state transition table. Is also, we have already seen input, output, like that, input, and then number of states will be here, like that. So let me take one example. But how to represent this finite automata means you can represent this finite automata either in state diagram form or else in state transition table. So once you have these two, right, you can easily, solve half of the problem. Like if you find any error, right, you can check where I'm having the error. Okay, half of the problem is being solved once you know how to represent a finite automata. Now let me move back to the slide. So in this slide, right, if you are finding it, it's a bit complex to understand, don't worry. I have just taken some text from other source. Don't worry. Let me just take one example about finite automata. But let me complete this slide first. And then one more thing, next line, right? It is saying the recognizer for this. It's nothing but the language which is going to be. Oh, wait. Let me move here. Here I have mentioned that finite automata will be accepting one language. Okay. So this L1, I haven't mentioned the name. So the name of this L1 is nothing but regular language. Regular language. The language which is going to be accepted by finite automata is known as regular language. Okay, that's what the slide contains, right? Recognizer, this one. Don't, okay, wait. Many people are trying to join the class. Let me just submit it now. So the name of the language which is going to be accepted by finite automata is known as regular language. One more thing, do not complexify the thing. If it is hard, just inform me, okay? So the language which is going to be accepted by finite automata is known as regular language. And then there are two types. I explain what is this deterministic and okay. And next slide, yeah. This is the mathematical definition of deterministic finite automata. This is the mathematical definition of deterministic finite automata. And then let me just inform you capital what do we mean by capital Q, this. Let me take one example straight. Don't get confused. This is not very complex. It's very simple. Once you start understanding, it's very interesting. Don't get confused with these symbols and all, okay? In order to explain this symbol, capital Q, these things, right? Let me take one example. Let me take one example of a finite automata. And then as with that example, let me extend this one. And then you guys might be thinking that ma'am have been dealing with finite automata, but directly it started with deterministic finite automata. Okay, do not get confused. Let me take one example and then let me explain these symbols. That will do the work. Okay. As per the mathematical definition, we have seen just now, capital Q, summation Q naught, this, and then what else? This. Wait, let me check whether capital F or this one. Okay, capital F, it's inside. It's nothing wrong, you can keep this one. I'm not convenient with this right now, okay? Bear with me. If somebody is trying to join the class. Now see here. This represents set of states. This represents set of states. This represents set of alphabets or input symbol. Alphabet or input symbol or input symbols. Input symbols. Okay, and then this represents set of final states. Final states. Okay, and then this is known as transition function. This is known as transition function. Now, I have already mentioned that there are two types of machine, deterministic and non-deterministic. Depending on this transition function, you can able to identify whether this machine is deterministic or non-deterministic. Now, in the previous lecture, I mean just now, a few moments, right? I have just mentioned that you can represent a finite automata either in state diagram or in state transition table. Let me tell you one thing. In Chandrasekharan textbook, right, they are representing all the finite automata, all the machines using transition table. But I prefer this state diagram. Okay, I'm interested in state diagram, so I'll be using state diagram to represent a machine. Now let me take one example here. Let me complete the example. Wait a second, it got stuck. Okay, it's fine. One. Okay, this is one finite automata. Let me explain you. Capital Q represents set of states. In this state diagram, number of, what are the states represent here? This circle, right? Q naught, and this is double and circle one. Leave it for the time being, just see how many states are there, Q naught and Q1. So as per this one, right? Then why am I using curl? Set of states means set of inputs or alphabets, right? So in this here, inputs are 0, 1, hands like this. Next, in certain textbooks, right, it's Q naught. It's not that initial state. Oh, I haven't mentioned. Sorry. This is Q naught is the initial state. Initial state or start state. It's fine. It's not that initial state will always have to be, Q naught. It may be Q1 or Q naught. But how to identify an initial state in the given state diagram means this incoming arrow is there, right? This is indicating that this state is the initial state. So if it is Q1 and then if you have an incoming arrow like this, then this state is representing an initial state. Okay. So okay, fine. Initial state is Q naught. So let me write like this. Now, even though this is F, set of final states, but here, as per my state diagram, only single final state is there. Even though if it is single, but do not write Q1s alone, because capital F is representing a set of final state. So you have a set which is going to have a single element, which is Q1. You have to write like this. And next one is transition function. So this transition function, right? Let me write like this. And then where this, okay. Sorry. This has to be only double dot, okay, not triple. Okay. This is dot, okay. Now let me, before I start writing this transition function, let me explain this diagram, this state diagram. What kind of finite automata I'm designing right now. So initially Q naught, if you have an input symbol 0, then it will not change its state. It will remain in the same state, which is Q naught. And the state is Q naught, and the input is 1, right? Then it will change the state from Q naught to Q1. So this H, right, this is known as H, and the H, we have one level input, which is 1. So when currently at state Q naught, if the input is 1, then it will perform the transition from Q naught to Q1. It means that one. And then now currently at Q1, if you have an input 0, then it will remain in final state itself. Again, from Q1, right, if you have an input, it will perform the transition from Q1 to Q naught. So let me start the writing the transition function. How to write the transition function? This is also very important. Currently Q naught, input symbol is 0, then it will remain in Q naught. Okay, this is how you should write a transition function. This is first transition function out of this particular diagram. So let me write serial number 1. Next, serial number 2. Currently at Q naught, if the input is 1, then it will perform the transition from Q naught to Q1. Serial number 3. Serial number 3. Q1, input 0, then Q1. Serial number 4. Q1, 1, then Q1. And let me remind you one more point here. write, how to define a given finite automata using the definition which we have just seen right now. So let me just have a glance. Set of states, this is capital Q, this is capital Q, this is summation, this is initial set of final states, function. So let me move back to the slide. And then once we start understanding the symbols and all, right, I'll be explaining what kind of machine we are designing here, what kind of language they're going to accept it, they're going to delete it, we'll be discussing later. Okay, for the time being, why I'm designing this machine means I'm just teaching you how to define a given machine using 5 tuples. How many attributes are here? 1, 2, 3, 4, 5. Instead of saying this one as attributes, right? Each one is going to be called as tuple. That's why 1, 2, 3, 4, 5, 5 tuples. So let me move back to the slide. So in this slide, have you seen this one? A deterministic finite automata is defined by the 5 tuple. 1, 2, 3, 4, 5. And then regarding this capital Q definition, summation, Q naught, capital F, then transition function, no need to explain the contains out here. Okay, I have directly taken one example here, and then from this example, I have written the corresponding values of this capital Q, summation, and all. Okay, I guess you have understood this one. And then next, let me move back to this slide. Okay, see here. This is the block diagram of a finite automata. In your textbook, right, they have inserted this symbol, CS. But in my opinion, right, doesn't need this. Okay. In certain textbook with Indian author, in any other Indian author, right, they will not be showing this capital C and S. In your textbook, which I've already uploaded, they have drawn the block diagram like this. That's why I've taken this block diagram from the textbook itself. Okay, don't get confused. This is an overall diagram of how a finite automata looks like. They have a reading head, finite control. We have already seen in digital design paper like Q naught, Q1, this control will control the movement of one state to another, that's it. And then this is known as sail. Okay, all these summation, the elements from the summation will be inserted here, and then this reading head will be reading the input symbol from this, like currently this one. Currently, let me write something here. Currently at Q naught. Okay, consider that nothing is here. Nothing is here. It just start from here. This is Q. Wait. Sorry. This is not Q. This is 0. Currently at Q naught, and this is moving towards right side. One restriction is there. This reading hat, right, it cannot move towards the left side. Okay. One restriction is there. It has to move only towards the right side. So let me explain it. Currently at Q naught, after reading this 0, the reading hat will move towards the right side, and then the state is still the same, which is Q naught. Okay. Now this finite control, right? If currently at Q naught, if the input is 1, it will move towards right side, but it changed the state from Q naught to Q1. And Q1, if the input is 0, in this case, in this explanation purpose, right, what I have done here is, as per this states, I'm inserting the input. It's not like that. Already this inputs will be already there. Let me take one example with this Q naught, then it will be Q naught, Q naught, Q naught. Okay, so now let me just check. Okay, let me move back to the this one. Now see here. Let me draw the block diagram here. Let me take a string 0, 1, 1, 1. Initially, it should always start from initial state, which is Q naught. Okay. Now, currently at Q naught, input is 0. Then it will move to Q naught again. Q naught, the the input symbol is 1, then it will move to Q1. Q1, if the input symbol is 1, it will move to Q naught. Q naught, if the input is 1, it will move to Q1. Okay. Or else by hash symbol, got it. This is how we are this is the example that. Now let me move back to the slide again. Okay, next is transition system. Whatever is the content here, right? Please avoid it. Let me just move to the the finite automata. So this transition system, right? I'll go to the. Okay, fine. It's like a graph. It consists of edges. Then somebody is trying to join the class. Let me just. Okay, see here. This transition system, right? I'll just avoid the content of the slide. Let me move to the next one. This is one diagram, this input output. I guess many of you have seen millimole input output, these things and all. Leave it. I'll just take the same example, don't worry. I'm just showing you the slide, content of the slides. Okay. In this transition function, it got stuck. Okay. Okay. This transition system, right? Let me explain you. These are the contents out here. Let me just explain you. And then this is very important. Q1, this is very important. I'm just drawing a line here. Let me move back to this page and then let me explain. Now see here, I have already told that finite automata could be represented either in state diagram or a state transition table. And then regarding the state diagram, right? This one, state diagram. The state diagram. The backbone of this one is the transition function. Okay, in this transition function, they are showing if the input is being read as 0, then where it will perform the transition. So this transition system, right, is very important. We need to understand in terms of finite automata. Okay, and then let me explain another term. Just now I have just drawn one line, remember? So let me write the same here. Delta rho. Okay, let me just write Q naught WW Q1. Okay, let me just explain this. In this case, let me take W. W is representing a string. In my example, the input as consists of 0 and 1, input symbol, this summation, right? It consists of 0, 1. So let me consider a string which consists of 0 and 1 alone. So in my case, let me take 0, W string is equal to 0, 0, 1, 0, 0, 1, 0. Okay, so let me rewrite this transition function again. Q naught 0, 0, 1, 0, 0, 1, 0, Q1. Okay, now I'm going to check this string related with this particular state diagram. So let me rough this part. Now W is equal to 0, 0, 1, 0, 0, 1, 0, 0, then 1, 0. Okay, I'm going to check. Now see here, let me, every transition, right? Let me try to represent with this arrow. 0, 0, 1, 0. Okay. This always like initially where the reading hat will start means it will start from Q naught. Okay. Now currently Q naught, if the input symbol is 0, then where it will perform the transition? As per this diagram, if the reading head is at Q naught and the input symbol is 0, then it will not change state from Q naught to any other state. So it will remain in Q naught itself. So let me write Q naught. Okay. Now again, still the reading head is still in Q naught, and then input symbol is 0. Hence, it will remain the same. So let me write Q naught here. Now current state is at Q naught, but the input symbol is 1. So 1 means it will perform the transition from Q naught to Q1. So let me write Q1 here. Now currently at Q1, if the input symbol is 0, it will remain the same. It's a self loop, okay? So it will be in Q1. Again, currently at Q1, if the symbol is 0, then same here, Q1. Now Q1, but the input symbol is 1, then we'll change the transition from Q1 to Q naught. So let me write Q naught here. Now Q naught, this will be Q naught. Okay. Now let me rough this part because it's of no use. Let me just rough it. Okay. Now see here. Delta Q naught. Q naught means the initial state, and then W, the string here, Q1. Now let me just rewrite it. This Q naught 0, 0, 1, 0, 0, 1, 0, comma Q1. Okay. Now let me move back to the slide. See, as per this diagram, right? Initially, it starts with Q naught, and then certain strings we are going to consider here, and then we'll check the transition how I've just done right now. So we'll check it, and then as per this statement, it means that the graph starts at the vertex Q1, goes along a set of edges and reaches the vertex Q2. The concatenation of the level of all the edges thus encountered is W. Okay. So this part I'm just trying to explain with the example which I have just taken right now. Okay. As per this example which I have just taken the string, right? As per this example, it starts with Q naught. As per this string, it starts with Q naught. And then I've checked the transition from Q naught till the end of the string. While reading this input symbol individually, right, I have seen certain transition from Q naught to Q1 and then from Q1 to Q naught. That is the statement here. So as per this one, right, when I perform the transition, when I check the string, when I read the input one by one, right, this is not Q1. I have started from Q naught and then it has ended at Q naught. Okay, I'm just explaining what's the meaning of that underlined term. It's not like we are checking whether it's true or false. It's not like that. I'm just explaining what does the term mean to us corresponding with this particular example. Okay, so again, let me move back to the slide. So this underline meaning, right? I've just considered an example there, and then I have explained to it. Now next one, this one again, no need. This two arrow, remember this one, Q0, Q1. These two circles, right? These two circles, they're representing the state, and then Q0 also one there, Q1 also as per this transition to initial state, which are Q0. Okay, and remember this is not deterministic finite automata. About a transition system. In the case of transition system, you can have more than one initial state, but in the case of finite automata, you cannot have more than one initial state. When I talk about finite automata, it means both deterministic and non-deterministic. You cannot have more than one initial state. Right now, I'm talking about a transition system. In a transition system, you can have more than one, but in the case of finite automata, you can't. Okay. Next comes about the what acceptability of this string. Okay. This is, I have already told this has been taken from your textbook. So let me explain the acceptability of a given string depending on my example, which I have just drawn right now. Okay. Now, in order to check the acceptability, right, let me just take another string. Let me just rub this one. Let me just take another string. And then whatever string I'm going to consider, right, it will be checked based on this diagram which I have just drawn here, this one, finite automata. So let me take one string here. Let me consider this as W1. Let me take another string which is represented by W2 is equal to 1, 0, 0, 1, 1, 0. Okay. So obviously, initially, it has to start from, let me draw it differently. Okay, let me draw from here. Let me write the input here. This one, the way I'm drawing this one, right, it's not correct. Okay, but the way I'm checking the concept will be same. Let me write the input here, 0, 0, 1, 1, 0. So I'm going to check whether W2 is accepted by this machine. So it has to, how to check means, it has to start from Q0. Let me write Q0 here, because why I'm always starting from Q0 means, as per this diagram, Q0 is the initial state. So Q0, if the input symbol is 1, it performs the transition from Q0 to Q1. So let me just write Q1 here. And then Q1 input symbol 0, then it will stay in Q1 as it is. So this one also no change, Q1 as it is. Now Q1, if the input symbol is 1, then it will perform the transition from Q1 to Q0. So let me just write Q0 here. And then currently at Q0, if the input is 1, then transition to Q1. And Q1, then 0, this is Q1. Now, let me just rub this. Let me just rub this. Now see here. 0, 0, 1, 0, 0, 1, 0. This is Q naught. This is Q naught. This is Q naught. Q naught. I'm not. Jagdeep, mute your mic. Mute your mic. Now see here. W1, I have checked the, I have did the input one by one, and then I have checked the transition function. At the end, it is Q naught. At the end, it is Q naught. Okay, after performing this transition, right? At the end, the ending state, it's Q naught here. And then after checking this W2, right? Initially it starts from Q0 and then at last it is Q1. The ending state is Q1. Now how to check the acceptability of this string W1 and W2 with reference to this state diagram is, after checking this transition, series of transition functions, right? It whether it belongs to set of final states or not. Set the final states, right? With reference, this particular state diagram is Q1. So Q0 does not belongs to set of final state, but Q1 it belongs to set of final states. So hence this particular diagram, right? Let me number it as figure 1. So W2 is accepted by this machine, which is drawn in figure 1, but W1 is not accepted. W W1 is not accepted. It's not accepted by the machine drawn in figure 1. Okay, that's the end of today's class. And wait 1 second. Wait 1 second. Just wait for 1 second, okay? Okay, fine. That's the end of today's class. Just go back and do some reading, okay? Now let me end it here.